Hello everyone, my name is Davide and I'm an applied scientist at Facebook AI. Today, I'm excited to talk to you about differential privacy and how you can use it to train models with PyTorch. Let's go over the agenda real quick. We're going to start off with an introduction to differential privacy. We'll follow up with a more in-depth discussion on how to use it with machine learning and with PyTorch, and there'll be a demo on Colab. And finally, we'll conclude by talking about the awesome ecosystem that has formed around this project, and I'll point you at some more resources if you're interested in following up. All right, so what is differential privacy? Rather than throwing a definition at you, let's look at the problem that differential privacy can help us solve. This is a collection of data, with each data point being an image. What we want to do with collections of data like this is learn something valuable from them, something interesting that becomes visible only in aggregate. But let's go back in for a second. We have a ton of resolution here, and we're able to see each individual data point. But do we really need all this much information if all we care about is actually just the aggregate, just the Mona Lisa? Could we do something like this? Here, we have greatly reduced the resolution into the images, so much so that we aren't able to say what they contain anymore. We have preserved the privacy of those images. But now the real question is, of course, what about doing our job? What about the aggregate? Let me just show you. The answer is remarkable. Almost nothing happens. To do your job, you don't need this much information from each and every of your training samples. This is the core idea behind differential privacy. By destroying a controlled amount of information, you get to have your cake and eat it too. You get to preserve both the privacy of your training data, as well as still be able to do your job, still be able to obtain the aggregate that you care about. And this is what made differential privacy the gold standard in privacy protection. So much so that it has been used by the US Census Bureau for the 2020 census, and it has been recognized by the European Union under GDPR. I mentioned aggregates previously, and that was a vague term. There is a reason for it. It's vague because aggregates can really be anything. They can be as simple as counting stuff or computing a mean, or they can be as complex as training an advanced machine learning or deep learning model, which is what we're going to talk about now. One important thing about these models is that they memorize, and we should really be careful about memorization. In fact, memorization violates privacy. Don't believe me? Let me show you this. The image on the right was extracted from a classifier that was trained using the image on the left. I want to iterate one point. This was a classifier. It was not a GAN, it was not a generative model. This was a classifier that would read an image and classify what person it belonged to. So the information about the training set can be extracted from a trained model. And this is why it's important to think about privacy. So how do we make machine learning more private? Well, we're here, so you can imagine that, of course, the answer is going to be with differential privacy. So rather than asking the what, let's ask how. And it turns out that differential privacy can actually be added at any point in your model's lifecycle. In the previous example, we added it to the data, and that's fine. You can also add it to the training algorithm or to a trained model after the fact, or even to a model's predictions during deployment. The gold standard is to do it during training. And it fits PyTorch perfectly, so that's what we're doing. PyTorch has made it simple to train advanced models, and now we're extending the simplicity to private models. We built a library for this. It's called Opacus, and it's a library to limit memorization. Opacus is the PyTorch domain library for differential privacy. We built it so that it's fast, it's safe, and it's production ready. To show you what it is and what it does, let's switch to Colab. It's much easier to show you stuff there. And of course, my video on Colab cannot be interactive, so we've also published the actual notebook for you to play with at this address. Let's see how easy it is to convert a project of yours to be trained using differential privacy. To get us started on the notebook, I have already written a bunch of import statements, as well as define a dataset and data loader. We're just going to train a model on CFR10. I have also defined a model architecture already. We are going to use a small model. This way, this demo trains fast, but of course, Opacus works with any model. And just to get started, let's train without privacy by writing a conventional training loop. This is all standard stuff. We're going to iterate through our data in batches, move the batch to CUDA, compute the loss, compute the gradients, and have the optimizer update the parameters. This works indeed, and we're hitting about 28, 30 iterations per sec, and we are able to complete an epoch in less than 10 seconds. Great, so far this has been the PyTorch we know and love. Now let's see how to make it more private. All we need to do is import Opacus and define a privacy engine. This abstraction takes care of applying differential privacy for you behind the scenes. It just needs a bunch of parameters such as your model, batch size, total data size, plus some privacy-specific parameters. Alpha is the range of any differential privacy orders that the accountant can use to compute your epsilon. Noise multiplier is the parameter you want to tweak the most. This is the standard deviation of the Gaussian noise that you're going to add to your model's params. And finally, max grad norm allows you to tweak the clipping threshold for each sample. If the gradient for any given sample exceeds this value, it will be set to this value instead. And we get a warning. Don't worry, this is entirely normal. We expose an option to turn on secure RNG for production runs, but it comes with a performance cost, so we keep it off by default. This way, we don't slow you down during experimentation. Once you construct your privacy engine, all that's left is attaching it to the optimizer. And once this is done, the privacy engine will be notified by the optimizer whenever anything happens. And you don't need to change your training code to make it private. In fact, we can literally just go ahead and copy-paste the exact same training code that we used before. Put it down here, and we can see that indeed, this runs just fine. And there's a small performance cost. We were able to hit 28 before, and now we are at 26 compared to 28 iterations per sec. The privacy engine will also remember everything that it did, and it can return the privacy expended at any given point in time. So in this case, we have returned epsilon equals 1.48 for alpha equals 11. Okay, let's switch back to the deck. Finally, I wanted to talk about our community because the response has just been amazing. We launched only on August 31st, and it was fantastic to see that we have already hit more than 600 stars on GitHub. We have more than 1,000 monthly downloads last month. And finally, more than 200 of you have already cloned this repo and tinkered with it, which is just a testament to how popular privacy-preserving AI is becoming, which is very comforting. Speaking of stars, this is the growth of our stars over time. We found it quite interesting. There's two fun things about this graph. One is that you can clearly see when we officially launched. And two, it's just remarkable that about 200 of you actually found us when we were still called PyTorch DP under a different repo, Facebook Research, and already actively engaged with us. In fact, there are even a couple of papers that we found that already use this software in this form. So thank you for alpha testing this with us. We took your feedback to heart, and a lot of it made its way into what became Opacus. So thanks. And finally, shout out to one of our key collaborators, OpenMind. They are a community of thousands of developers who are building applications with privacy in mind. As part of our collaboration, Opacus is becoming a dependency for their libraries, such as PySift. And they recently wrote a couple of tutorials on how to use Opacus. There's one on how to use Opacus in general. It's called Differentially Private Deep Learning under 20 lines of code. And recently, they wrote another one on how to use it with PySift to achieve differentially private federated learning. Thank you, Kritik and Theo, for writing those tutorials. And hopefully, I have piqued your interest in these few minutes that we've had together. If you want to get your hands dirty and start playing, I recommend you just start with our website, opacus.ai. We put a bunch of stuff to get you started in there. There are a bunch of tutorials, examples, FAQs. Go check it out. We're also working on a series of mediums that will act as from a gentle introduction to the core concepts of the PSGD, and they will take you all the way to more advanced concepts, both in the software engineering behind it as well as in the theory. The first entry is out, so I recommend you check it out. Help us make AI more private, and thank you.